The main part of this class is going to focus on common mistakes in SQL. There are two more parts to this presentation. The second one is going to focus on things you can do to make your SQL run faster. I'm going to focus on things you can do that don't require schema changes to your schema. I'm assuming that you have read access to your database. And finally, we're going to finish off with a little section about how to be more productive writing SQL. There's some tips I can share that will make you write SQL, which is more maintainable, easier to read, and hopefully faster to write. Okay, so I just want to say that this class is going to be a bit different. I don't like to just give lectures. I believe that the best way to learn is by experimenting. So I'm going to focus a lot on showing you code, sharing code with you, and I want you to participate by actually writing some SQL yourself. The insights I'm going to share with you are insights that I didn't just draw off some documentation page. These are mistakes that I see every day when I do code reviews for my developers in my team, when I review queries written by PMs and project managers and other managers in dashboard tools, and with suppliers I work with, and from people who just approach me online with questions they have. So these mistakes I'm going to present are actual real-life mistakes that I encounter every day. So hopefully you'll participate, and I would be very happy to hear about whether you encountered any of these mistakes, these errors, and if you have any more things that you think you want to share with the rest of the class. Okay, so before we begin, a very, very quick overview of the history of SQL. I personally really like to get to know the history of the tools I'm using. So SQL stands for Structured Query Language. There's a lot of debate whether it's pronounced SQL or SQL. Well, on that, it used to be SQL, and then at some point, they found that it's a registered trademark, and they changed it officially to SQL. So the next time you have some office trivia, you're good to go. SQL was conceived back in the 70s, inspired by work by a scientist called Code, who worked at IBM. SQL is a language to interact with relational databases. You might see it as RDBMS. I know that there's a lot of other types of databases out there, like key value, document stores, graph databases. It can be very confusing, but RDBMS are the most common type of database out there. So in '86, they drafted the first standard for SQL called ANSI 86, and in '92, this standard got a major revision, which contains most of the language features we know today. The reason I'm telling you this is because you may often encounter these ANSI 92 and ANSI 86 when you evaluate new databases. So now you know what they mean. As you saw in the class brief, we are going to focus on PostgreSQL. PostgreSQL is a free and open source database. You can see the chart in the bottom right that it's growing very, very fast. This is one of the fastest growing databases out there. It's very, very fully featured. And as I said, it's free and it's open source. So we are going to use PostgreSQL today for our class. To finish up the introduction part, let's just go over real quick about the SQL query and the anatomy of an SQL query. So an SQL query usually looks like a select from, where, through, by, having, and order by. But this is not actually the way the database executes your query. So I want to do a little first attempt at interacting with the group. So I'm asking you, what is the first thing the database does when he sees your query? Which of these clauses are evaluated first? please take a second and answer this in the group chat. I just want to make sure that you're live. So we got select, from, where. What is the first thing? Okay, I see some comments. Great, great. LIGV, that's right, LK. Amazing, exactly. So the first thing the database does is doing from. It needs to know where to fetch data from. So what's the next thing after from? What is the next thing the database does? Right after from. From where select. Exactly, from where. That's right. From is the first thing the database does. Next, it applies any conditions in the where clause, also known as predicates. The where clause can also sometimes contain a join. So the database first fetch the tables, and then it needs to apply the conditions to join these together. The next thing, as somebody already mentioned, is select. Right, from where select, and then after select, what is happening after select? Group by. That's right. That's right. Right after applying or selecting a subset of, right after selecting the data from the table, it can apply the group by. The having is working on the results of the group by, and finally, you can sort by, order by. That's right. So we have a, great, that's great. So as you can see, we have from, where, select, group by, and having, and finally order by. That's great. So just to warm up a bit, let's take a look at this imaginary query to count the number of employees in every department. What is the problem with this query? So this query is trying to fetch the number of employees in each department, and then it applies a condition to only get departments with more than 10 employees. What's wrong? Exactly. Select is evaluated after where? Redundancy of count. We should use having. Exactly. So if you keep in mind the order of execution, we try to apply condition on the number of employees, which is generated by the group by, but we are trying to do that in the wrong place, because when where is evaluated, we don't have the number of employees yet, because this is calculated by the group by. Great. So as some of you already mentioned, you can apply a condition on an aggregate in the where. You need to use having. Exactly. You are all mostly correct. And we are good to go with the first part of our presentation. I want to take like a minute or two and have you set up your environment. So you have several options here. First, if you have a local database, then you can check out the GitHub link. There's a script there. It's called Schema SQL. You can just paste it in some database. I'll try to show it to you, okay? This is also going to be the first time I'm going to share my screen. So you can just log into the PostgreSQL and paste the script, and you should have a sale table, okay? Now, if you don't have a local database, you can use, can you send us the link? Yes, of course. If you don't have a local database available, there is also a service called DB Feeder. I already set up the database for you. You can just, okay, so first this is, let me just paste the link to the repository here. Okay, you can go to this repository and get the Schema SQL script. For those of you who don't have access to a database, you can use DB Feeder. It's a website. Here's the link. All you have to do is make sure that the database is Postgres V12. And when you hit run, you should see the results at the bottom of the screen. Now, The left part is a schema SQL. You should not be touching it too much. You will write queries on the right side. Okay, it's titled Query SQL. When you press Run on the top, you should see the results at the bottom. Now, I highly recommend that if you have a local database, set it up locally. I want you to experiment with the tools that you are used to working with. So let's take a second. I'm going to give you like 2 minutes. Okay, let's take 2 minutes and set up the database. Please let me know in the group chat that you are ready, either with a local database or with the db-fetal. For those of you, in the meantime, for those of you who are just listening in or don't, for some reason, are unable to set up a local database, I'm going to show you both with share screen and in the presentation all of what we are going to do. So worst case scenario, you can just follow along with the presentation. It's totally fine. I strongly recommend setting up a database, but if you can, that's also fine. This is our table. It's a sales database. I use sale because it's very common to have like a sale transaction table in the database. Let's go over the field and make sure that we are understanding the data in the database. So first we have the ID. This is the primary key of the table. This would usually be sequence or serial number. As you can see, it's unique. This is the primary key. Next, we have the branch. We have two branches. We have the New York branch, which is marked by NY, and we have the LA branch, which is marked by LA. Usually in tables like sale, data like branch would be a foreign key to another table. In this case, I decided to use just text because it's easier if we work with text, but this can easily be a foreign key to a branch, like a branch ID with 1, 2, 1 stands for New York, 2 is LA, 3 is whatever. But for simplicity, I use text. And next we have the sold at. This is the time the sale was made. You can see, for example, the first row was made, the first sale number 1, was made in the 31 of March 2020 at 8:15. Next, we have a column called customer. This is, once again, a field that would usually be a foreign key, but for simplicity, I use the name of the customer. So we are going to assume that customer name is unique for customer. So Bill made 3 purchases. Okay. Now, as you can see, some of the customer values are null or empty values. You can see the blank pages, blank areas in this column. We are going to refer to these null values as unknown customers. Think about a customer walking into a store, and if he has like a membership card, then I know his name, I know it's Bill, and I can mark the sale as one that was made by Bill. However, if I get like a walk-in from the street, I don't know who this guy is, so I just put null. Okay. Next, we have the product column. Once again, this should be a foreign key, but I kept the text for simplicity. We have different types of products here. Then we have the price. The price is the full price of the product, the full price of the sale, okay? And the discount is the amount of discount from the full price. So Bill, the first sale, is for $100. You might notice that I use cents to represent the price. It's usually a good idea to use full integers for price and not using double or floats. So I'm using cents. In this case, it's $100, and the discount is $10. So the discount rate in this example is 10%, and Bill only paid $90. Okay? So this is our table, and what we are going to do is we are going to run different queries on this table, and hopefully we can identify different mistakes that people usually make when they write queries. So Let's dive in to our first exercise. Why wouldn't you just use decimal or float? Okay, I'm going to take just 1 second to show you something fun, okay? So this is why I usually don't use decimal for prices. For example, you would expect that that should be true, right? But in fact, this is false. There are a lot of funny stuff going around when working with decimal and double numbers. Also, if you think about it, there's no such thing as half a cent. But I'm usually not a big fan of using floats for anything, unless it's really necessary. But money, I think, is very sensitive, so I use full numbers. We can talk more about it later if you want, but I want to move on. So the first exercise, what is the discount rate on shoes? I want you to write a query that finds the discount rate for each sale of shoes. So for example, in the first row, the full price can be used double. They are all equally I generally recommend using full numbers for integers, but depending on your use case, you can use whatever works for you. I never use double and floats for money. So back to the exercise. We want to find the discount rate for each sale of shoes. So for example, in the first sale that we've seen before, the discount is $10 and the price is 100. So we want to get 10%, right? 10, which is 10%. So take 1 minute and try to write a query that will add a discount rate field with the calculated discount rate for each sale of shoes. Let's try to do like a naive implementation of this query. Let's write it together, okay? So, window here. Okay, so we want to get the price and the discount, right? And we want to get the discount rate, which is discount divided by the price, right? And we might want to multiply by 100 to get the percent. Now, we only want shoes. So we apply a filter, and this should work, right? Okay, so this is interesting. We got the price, we got the discount, but the percent is 0. Did anybody get zeros? Okay, so I see some creative solutions around 0, but did you actually get the discount percent you expected? I'm guessing that at least some of you got 0. Okay, so let's try to see what's happening here. Once again, I'm going to share my screen, and let's try to break it down. So what happens is that the type of the number is integer. And if you divide an integer by an integer, you get an integer. So PostgreSQL will truncate the integer, and you will get 0. If you want to get a fraction or a floating or a double result, you need to cast one of the sides to float. So if you do 1 divided by 2 as float, you will get the expected result. And then we can multiply by 100 and get percent, right? So if you want to write the query again, we can do select price, discount, right? And then discount divided by the price, and we are going to cast it to float. Sorry, yeah. That's what we wanted. And next, we can multiply by 100 and get the percent. Okay, so let's go back to the presentation, and you can see that when we divided two integers together, we got a truncated result, which is integer. Great. I see some people got 0. That's great. Exactly as I anticipated. So if we want to get a float, we need to cast one of the sides to float. In this case, we cast the denominator to float. So you can see that 10 divided by 100 gives you 0. But if you cast one of the sides to float, you get 0.1, and multiply by 10, you get the percent, which is 10%. This is great. If you put it all together, this is what you get, then multiply by 100, and we get the expected result. Okay, so now I want for you to find the average discount rate by product. You already know how to find the discount. Now I want you to find the average discount rate by product. You need to use group by here. So I'm expecting 5 rows, one for each product, with one number for each product with the average discount rate. Okay, so I'm guessing that some of you might have written it like this: select product and the average discount divided by price. We already know that you need to cast one of the sides to float and then multiply by 100 to get the discount rate, right? The difference here is that we use product both in the select and the group by. And you should get division by 0, right? So this is very common. Let's once again see what it looks like, right? So division by 0 is what we get, the exception that we get when we divide something by 0. Like this, for example, 1 divided by 0 is causing a division by 0. One way to avoid this mistake is to use a very interesting character of the database. Apparently, when you divide something by null, the result is null. So maybe we can use that fact to completely avoid this division by 0 mistake. So if we try to turn any, first of all, let's see what the table looks like and see why we are even getting this mistake. So we have a sales table, and we can see that there's a product called giveaway, which the price for this is 0. So if we try to calculate the discount percent for a giveaway, we are going to try and divide the discount, which is 0, by the price, which is also 0. This is what's causing us the division by 0 mistake. So as we said, we can try to turn any 0 price into null. Let's try to do this right now. First, price, discount. Let's try to get the product first, price and discount. And now we want a price that will be null if it's 0. There's a very useful function called null if, and the function receives 2 arguments. The first one is a value or an expression, and the second one is the value that if the first argument equals this value, will turn into null. So in this case, we want to turn price into null if it's 0. Let's call this adjusted price. And let's see what it looks like. So as you can see, in places where price is 0, the adjusted price is null. And in places where it's not 0, the price is not null. Okay? So now we can use that adjusted price to calculate the average, just as we did before, right? So we still need to cast to flow, and we can multiply by 100 and get the average of all of them, right? And take a look at that. No 0 division error. Great. So we are making great progress. As we said, we want to turn any price into null. We did that using the function null if. Now, the next question is this really correct? Is this what we expect to get? If we, for example, try to produce some sales report, do we really want to get an empty value here? I think that, and forgive me if you're like a math major or something, but I want to see zero, okay? Because if the price is zero and the discount is zero, I want to see that the discount, the average discount is zero, which means I didn't give any discount. So how can we turn how can we turn null values into another value? We can use another useful function, which is called coalesce. Coalesce accepts any number of arguments, and it turns, I'm sorry, my screen share just stopped working. Never mind, let's stick with the presentation for now. So there's a function called coalesce. It accepts any number of arguments, and it will return the first argument, which is not null. Okay, so in this query, you can see that we use coalesce and surrounded the entire expression. And when this expression, the average discount rate, is zero, we give it zero. Okay, so the first argument is the expression. The second one is zero. And as you can see, the discount rate for giveaway is now zero. Okay, great. Now I want to move on to the next exercise. Hopefully you got it. We are going to come back to coalesce in a bit. So the next exercise I want you to do is find how many unique users purchased each product. Let me remind you, users with the same name are considered the same customer. Sorry, not user, customer. So how many customers purchased each product? For example, shoes, two customers, and etc. Okay, so we want to find how many unique users purchased each product. So some of you may have written this query. Let's take a look. Okay, so we want to find, for each product, we want to count how many distinct customers purchased every product, right? So let's take a look at the results. We can see that the product hat, for example, has 0 unique customers. This result is pretty strange. How is it possible that I have a sale in the database that no customer actually purchased? So this leads us to the next common mistake, which is often overlooked, which is that aggregate functions usually ignore null values. Okay, so we can see that the one customer that purchased a hat is an unknown customer. So the customer column is null. When we try to aggregate, we found 0. As you can see, when we did count all rows, okay, using the aesthetic, we got 1. When we counted the customer field, we got 0. But this can also be useful. Okay, so now I want you to try and count how many known customers purchased each product. How many known customers purchased each product? We want to find the number of known customers purchased each product. And we know that aggregate functions ignore null values. So we can use that fact to count 2 metrics. First, we can count the actual customer field and get the number of known customers that purchased each product. And we can also use the count asterisk, which counts the rows regardless of the values, minus the number of known customers, and get the number of unknown customers that purchased each product. So you need to be aware of the fact that aggregate functions such as sum, count, AVG, average, ignore null values. So if you apply an aggregate function on a field, you need to be aware whether it can be null or not. Okay, great. So if you don't remember everything, that's totally fine. The presentation is up on the repository, and we are going to do a quick summary in the end with everything we did. So you can lay back and just do the exercises. All good. Okay. Next, I want to imagine that you have like a dashboard, an application that lets you use placeholders. Okay, so I want you to write a query to find the sales made by the customer field. We want to write a query that finds sales by, right? So from sales where customer is billed. Okay, so it seems pretty easy, right? To write a select from sale where customer equals bill. Next, let's try and do the same thing, but this time I want you to try and write a query that finds the number sales made by unknown customers. I remind you, unknown customers are customers where the value is null. If you want to compare a field with null, you need to use is, right? Because if you try to use customer equals null, you will get nothing. If you want to compare with null, you need to use is, right? So this is kind of tricky, and let's see why. So back to this dashboard scenario, let's say that you want to write a reusable query using some placeholder, and you want to accept any valid value for this field and get the sales for this user, okay? So in this example, I'm using a PSQL placeholders. I saw many different types of placeholders. Usually it's curly brackets, square brackets, dollar signs for placeholder. In PSQL, you use this type of placeholder, okay? So if we set the name to bill and we try to select from sale where customer equals name, you get the expected results, right? If you try to do the same thing with null, you can see that set name null means that we now set the variable called name to null, and we try to fetch where customer equals name, we get nothing. So this is incorrect. We know that we have sales met to unknown users in the database, right? The question is, how can we write a query that can handle both literal numbers like bill and null values? So we know that null is null because we use is to compare null values. We know that null does not equal null. As you can see, the result here is null or unknown, also a unique value to PostgreSQL. Okay, so how can we write a query that will accept a variable which is both a string and a null? So we can try and write a more complicated predicate. You can see that this is what the complicated predicate looks like. If name is null and customer is null, this is the null case. Now, if the variable name is not null, we want the customer to equal the name, right? As you can see, if we try this condition with bill first and then with null, we get the expected results. But this is very long, very complicated. There must be a better way. Well, there is. To compare null values, there's a special comparison operator called is not distinct from. Is not distinct from is a special comparison operator that lets you treat a null like an ordinary value. So if we want to try and rewrite our query to work with both null values and string values, we can change the condition to is not distinct from. Customer is not distinct from name, which is our variable. So let's see it in action. You see, we set the name here to bill. So select from sale where customer is not distinct from name, okay? And we get the expected result. And with the exact same query, we can use null for the name variable, and we will get the expected result, okay? So you might have caught it earlier, but is distinct from has two forms. The first is distinct from, and the other is the negative, is not distinct from, okay? We can use is not distinct from to compare null values like arbitrary, normal values. In this table, you can see all the possible values. So take a look at the table on the right, okay? We have two values, A and B, and then we compare the result of simple equality, and then is not distinct from, which is the equivalent to equality, but it can handle null values, okay? So 1 equals 1, true, and is not distinct from, true. 1 equal 2 is false, and is not distinct from is the same. But once we get null in there, it gets complicated. So 1 equals null equals null. You need to use is not distinct from if you want to get the expected result. Same goes for two null values, okay? So when you are working with columns that are nullable, can be null, you need to be aware of this, and you need to make sure that you use the correct comparison operator. Okay, great. So the next part of our presentation is going to focus on dates and times. So dates and time. Dates and times is a very common use in databases. You want to calculate averages, values over time, you want to work with time series. So datetime arithmetics and datetime's handling is crucial to not making mistakes. So I want to start by doing a very ambitious experiment. And I want you all to try and find the amount of sales during each month. I want you to try and find the amount of sales during each month. You should get a table that looks like this. You want the month, March, April, and I want the number of sales that were made each month. To get the date from the timestamp, you can use a function called datetrunc. If you're not sure how this function works, I encourage you to look it up online. I'm going to give you 2 minutes to this exercise, and I want you to share in the group chat how many sales were made in March and how many sales were made in April. Okay, so let's try to do this together, okay? So this query, we want to first extract the month from our sold F, and we want to sum the price, right? So we get that in March we had 13,500 and 50,85 in April, okay? So this is what we get. Now I want you to keep this numbers in your head, and we are going to get back to them. Okay. So before we dive into what was wrong with this query, Friday, March 10, April. Okay. Okay. Thank you. Okay. So before we talk about dates and times, let's first understand how they are represented in the database. So there's a term called epoch. Epoch refers to the beginning of times in computer land, which is the 1st of January 1970. Okay, Unix time, which is what most databases use to represent date, is the number of seconds since epoch. You can see it in the database. If you do extract epoch from now, you get the number of seconds from the 1st of January 1970 in UTC time. The floating point is for microseconds. Now, fun fact about this date representation. If some of you remember the Y2K problem, there's another type of problem just like Y2K. It's called Y2K38. Mark. Yeah, I made this slide a while back. So there's a problem just like Y2K. It's called Y2K38. And most 32-bit systems that use signed integers to represent Unix time can only go up to 2038, the 19th of January 2038. So this is called the 2038 problem. So if you want to get rich very fast, you should try to come up with solutions for legacy systems for the Y2K38 problem. This is just an anecdote. You don't have to remember that. Next, we have time zones. This is something that is very important when talking about times and dates. Time zone. Two or maybe one time zone that we need to keep in mind is UTC, which is the primary time standard. This is not adjusted to daylight saving. There is a synonym also called GMT, which is the time in a place called Greenwich in England, which is interchangeable. You might hear GMT and UTC. They are the same. If you want proof, you can ask PostgreSQL. You see, if you take now at UTC and GMT, you see that I made this slide about a week ago. So time zones are represented as an offset from UTC. For those of you who work with foreign countries or in very large countries that span across time zones, the subject of time zone might be more familiar. But for those of you who work only in the local market or work in a country, you might not be aware of time zone. So time zones are represented as an offset from UTC. You can see in this example on the left that if you take Sydney, Tel Aviv, Paris, London, New York, you can see the UTC offset from each and every one of them from UTC, which is 0. So New York is -5 and Sydney is +11. Some countries even span multiple time zones. For example, the US has 4 different time zones. China, on the other hand, decided that it wants only one time zone. So there's some places you can cross the border and it's different time. So it's important to keep that in mind and when we are talking about time zone. So I want you to use the PG time zone names table and find your time zone. So take a second and get familiar with this table called PG time zone name. You can see the name at the bottom. And I want you to take a second and try to find your time zone name. My tea there. Okay, hopefully you find your time zone. It's important that you know your specific time zone. So to work with time zones, okay, when we are working with time zones, there are several ways to define the time zone for a specific date. For example, You can see that I want to take the 22 of March 2020 at 5 p.m. and I'm using American New York time. I'm using the type called timestamp TZ. We're going to talk about it in a second. This is one way to declare a time zone, date with time zone. Another way to work with time zone is to cast one timestamp with a time zone to another time zone. So for example, 2020 or the 22nd of March 2020 in American New York time converted to Sydney time. You can see that the time is now different. It's not 5, it's 8. You can see that with an expression below. You can take the now at time zone, Australia, Sydney. Okay, so these are just some of the ways to work with time zones. Remember the at time zone operator, and then you get the name. This is why I wanted you to find the name of your time zone. So, to make sure that we are all on the same page, take a second and find the name and the time in your local time zone. To get the time now, you can use the function called now, and then use at time zone and the name of the time zone you found before. But don't cheat. Don't look at the clock on the PC. Try and find it from the database. Okay, hopefully you found the time. For me, what's the time right now? At 3. Okay. So the next thing we need to keep in mind when we talk about dates and times is daylight savings. Daylight savings is a mechanism to extend the number of daylight hours during the day. So daylight savings is depending on the country. For example, in the US, they move the clock 1 hour forward or backwards. I don't remember which is it, in the second Sunday in March. So this year it was in the 8th of March, which was 2 weeks ago. You can see that if we convert the same time, for example, the 1st of March at noon, according to New York time, to UTC, we get 5 p.m. And if we do it 2 weeks after, we get 4 p.m. Okay, so this is caused by daylight saving, which will change on the 8th. And the reason I mentioned daylight savings is that it can produce pretty surprising results when in the day that it's transition. Oh, you can't hear me? No, working. Okay, I'm going to continue. So when you work with daytimes around the day that the daylight is moving either forward or backward, you can get some weird results. For example, if you take this the 7th of March 2020, you find that there was only 23 hours. So if, for example, you do some calculations that assume that one day has 24 hours, you can get incorrect results here. So you need to be careful and use proper arithmetics when working with time zone. So let's talk about database types. Okay, we saw earlier that we work with a type called timestamp TZ. Postgres have several types of dates. The first one is date. Date is a date without time. Sample use case for a date without time is, for example, birthday. Okay, birthday does not have a time, it's just a day, so we can keep it as a date. Another type is timestamp. This is date with time, but no time zone. The other type, which is the most popular type and the one recommended by PostgreSQL, is timestamp TZ, which is timestamp with time zone. If you look at the sales table that you are working with, you can see that the field sold at is defined as timestamp with time zone. I actually can't come up with a reason why you use timestamp without time zone, but if you're not sure, just use timestamp with time zone. This is your safest bet. Another very useful type of that provided to us by Postgres to do date arithmetics is interval. You can see three types of examples of using interval here. The first one is adding 3 hours. This is just English, like interval 3 hours. You can see a more complicated interval in the middle, like 3 hours, 2 minutes, 55 seconds. And the bottom one, you can see it's actually doing arithmetics with the interval data type. So interval 1 day times 3. So with 3 days, you can see that it's the 22 minus 3 days is the 19. Very useful. A more useful function is when you're working with date and times. First, the now. Now gets you the time now. You can use now and cast it to a date, and you get the date without the time. Another useful function is date trunk. You would usually use this function in a group by when you want, for example, to get just the month of a certain date. You can see an example here. You do date trunk on now, you get the first day of the month. Okay. You can use different times. You can trunk to month, hour. Another useful function is date part and extract, which work roughly the same, but with different syntax. You can get a specific portion of the date. So here you get the month, you get the day of the week, and with extract the same. Okay, so before, when I asked you to try and find the number of sold amount each month, I was really hoping for some conflicting results. So we can see here two similar queries, but each one is being executed in a different time zone. So on the left side, you can see that the time zone is set in the client by the user to America, New York, and on the right side, it's set to Los Angeles. If we execute the exact same query, we will get different results. Now, just imagine if we have like a nationwide store and we schedule a meeting in HQ about the sale, and the salespeople from New York come and the salespeople from Los Angeles come, and each and every one of them has different results. They work with different figures. This can be very dangerous. So this leads us to the first takeaway from this section. Time zone is usually set by the application, client application. So when someone from LA wrote this report, he got the results according to LA Times. And when someone from New York executed this exact same query, he got the results in New York time. So as we talked about before, this can be very dangerous. This can cause for major inconsistencies in results. So we need to be sure that we always explicitly set the time zone. So for your next exercise, I want you to find the amount of sales, not the number of sales, the amount of sales during each month. And I'm telling you, we are doing the billing according to America, New York time zone. Okay, so let's go ahead and do that. Take 2 minutes. This is very important. You need to be able to work with time zone. So take 2 minutes, and I want you to find the amount, the sum of the price, sum the price during each month according to America, New York time. Hopefully you got some results. So we wanted to find the amount of sales during each month according to New York time. So before, we got some conflicting results, and we found that the best way to work with time zones is to explicitly set the time zone. So the problem before was that we used date trunk to remove the time part from the sale date, but we didn't specify the time zone we want to work in. So this time, as you can see, we truncate the sold ad, but before we do that, we explicitly set the sold ad date to America, New York. So it doesn't matter on what type of client I'm running this query, I will always get the same results in New York time. Okay, so this is very important. And the reason I'm re-emphasizing this again and again is because I see endless mistakes when it comes to working with time zones. Every time you manipulate the date, you need to make sure that you explicitly set the time zone. So next, I want to do a different type of exercise, and I want you to think what is the best way to tackle this problem with time zone. So what is the busiest hour of the day in all branches? I want to find what is the busiest hour of the day in the entire network. Now, I want you to think about the fact that we have branches from different places in the US. We have branches in LA, we have branches in New York. So what is the best way to extract the hour for each branch? We want to find the busiest hour of the day in all branches. So once again, take a minute, 2 minutes, and try to find the busiest hour of the day in all branches. We want to find the busiest hour of the day in all branches. Okay? So the straightforward way, or I even say naive way of writing this query is to try and extract the hour from the sold at. As you can see here at the top, select extract hour from sold at, and then count the sales and group by the hour, right? And then we get this list. According to this list, the busiest hour of the day is 10. So if I'm like the CEO of this chain and I know that the busiest time of the day for me is 10, I might want to hire more staff to work this hour, right? And man the phones or whatever it is, because this is the busiest hour of the day. But is this correct? Is this really the busiest hour of the day in my entire chain? So the reason I ask this question is because when we want to find the busiest time of the day, we can't really do that in a single time zone. We need to work with multiple time zones. As we mentioned, we have several branches in the chain. We have branches in New York and LA. I chose these cities because, as I mentioned before, US spans across multiple time zones. So there's a big time difference between New York and LA. If we want to find the busiest time of the day, we need to cast or convert the sale time to the local time of the branch. So you can see here a slightly more advanced use of casting to time zone using a case statement. Let's go over this together. First, we extract the hour from the sold at column, and we do that at time zone and then case. When the branch is New York, we want to cast the day to New York time. When the branch is LA, we want to work according to LA time. And this gives us the hour of the day according to the date, according to the branch where the sale was made. And you can see on the right that we get completely different results. We can see that when we write the query the right way, we get that the busiest time of the day in our network, in our chain, is actually 11 at night. So if I was the CEO and you would bring me a report that says that the busiest time of the day is 10, and I hire more staff and man the phones and provide more support, but nobody comes, and then at 11 at night, I'm starting to get flooded with customers, I'm going to be pretty mad. So this is why it's so important to make sure that you always explicitly set the time zone when you are working with date and times. So I did a little summary of the common mistakes I see here. I see very, very often. I see this in dashboard reports, code reviews. The left column is the wrong way of doing it, and the right is the right way of doing it. The difference in all of these cases is that when you use a date, you need to, or when you manipulate the date, you always want to explicitly set the time zone for it. So for example, if we take the third example, sold at, which is a timestamp, and we want to strip the time part from it by casting it to a date, you can get incorrect results here if the time zone is not set correctly. The right way to strip a time zone from its time is to first set the time zone and only then strip the time part from it. So next I want to do another exercise of a very common problem I see all the time. And I want you to try and tell me how many sales were there in March. This time it's a number. I just want to count, not sum, count the number of sales that were made in March. So please take a second and try to write this query and tell me how many sales were there in March. I got a question from TY in the group chat. And while you are trying to find the number of sales in March, I'm going to answer the question. Why not just convert all the times to UTC times instead of doing place when then? That's a good question. As we've seen before, if I cast the reason we can't do that is that when we extract the hour from the time, the hour is just a number. It's not representing the time. What we want to do is we want to find the busiest time according to the branch. And the branch is located in a specific time zone. So the right way to answer this question is to cast the date to the time zone of where the branch is located, and only then extract the date, the hour from it. If you cast to UTC, you will get the busiest hour at UTC time, which is incorrect because you can't cast all the times to UTC because New York works in New York time, not in UTC. Okay? Hopefully, I answered your question. Why? Okay, so how many sales were there in March? You might have written something like this. Count from sale where the date is between the 1st of March and the 1st of April. Okay? You're now aware of the fact that you're now aware of the fact that you need to explicitly set the time zone, so you were responsible enough to set the time zone for each of the dates here. And you got that in March there were 9 sales. So next, how many sales were there in April? If you do the exact same thing, you just replace the dates, you see. We are fetching the number of sales since the 1st of April at New York time until March, New York time, and we get 7. Can anybody try and guess why this is incorrect? If we count the number of rows in the table, we get 15. But we found that March has 9 sales and April has 7. So it's 16. This doesn't make any sense. Can anybody try and think why this query is incorrect? This or the previous one. What's wrong with this query? Okay, so hopefully you are very, very lost and you have no idea what's going on. So let me explain. We use between, and between is inclusive. This means that both ranges included this time, the 1st of April 2020. And as we can see, there is one sale that exactly midnight. There is one sale that was made at exactly midnight. And this sale was counted twice. So this is very, very dangerous. we counted the number of sales in 2 months, and we got 16 sales, where in fact there were only 15 sales. And the reason for that is that we used between, and between is inclusive. So one sale fell into two ranges. The way to avoid this is to use what's known as a half open or half closed ranges. Instead of using between, which is inclusive, we can explicitly set the ranges so that they are half open or half closed. In this example, if you look at the top query, we want to count for March. We are counting all the sales that were made starting at the 1st of March, including, and until the 1st of April, excluding the 1st of April, as LK mentioned in the group chat, at midnight. We do the same for April, and we can see that we get correct results. 8 plus 7 equals 15, which is the number of sales we have in the table. So I know that this mistake is very unlikely in timestamps because for sales that are created by the user, the chance that someone would create a transaction at exactly midnight, 0.000 microseconds is close to nothing. But if you have automated jobs or batch jobs that create objects, they usually do that at round hours. And when you have transactions created at round hours, you might fall into this pitfall, fall into this very, very common mistakes. Now, between is inclusive not only for timestamps, but also for integers and dates with no times. So you can see at the bottom, for example, if we have a table of birth rates and we are looking for 90s babies, okay, we are also including everyone that was born on the 1st of January 2000. This is a much more common mistake when working with dates and no time, okay? So you should be aware of that, and you should be very careful when working with between. By the way, for those of you working with data science and machine learning, and you are doing binning or dividing results into buckets, this is especially dangerous if you're not using half closed or half open buckets. You need to make sure that you don't have any rows falling into more than one bucket or more than one bin, okay? So this concludes the first part of our class. And I want to once again go over the mistakes that you can now avoid. Hopefully, after you concluded this 1 hour and a half, you can avoid this mistakes. Now, before I go over the mistakes, I want to explain why I think these mistakes are especially dangerous. When you write incorrect query, you'll get an error, a syntax error. You know you made a mistake. When you write an incorrect query, you get the worst type of mistake. You get a mistake that doesn't throw any exception. You get a mistake that produces incorrect results. So you need to be very careful and very aware of what you are doing in order to even identify that you made a mistake. We've seen multiple examples in the past section that shows that you made an innocent mistake. You didn't get any exception, you just got results which made no sense once you looked at them. So my first recommendation is get to know the data. You need to make sure that when you write a query and you get the results, you need to make sure that these results make sense. So you need to look at the table, you need to look at the data, you need to look at the results. You can even try and pick one of the results and check them manually just to make sure you didn't make any mistake. The next part is to actually know the tools you are using. If you are using some kind of a function in the database, make sure to read the documentation and know exactly how it behaves under different circumstances. Okay, so the mistakes that we saw, I want to go over them. This is the summary I promised. And you have the presentation in the GitHub repository. And I also included a lot of links that you can use to get more information in places where it's relevant. So the first thing we saw is that dividing integers by integers truncates the results. If you want to get the correct result, especially when working with percents, ratios, you need to cast one of the sides to float. The next common mistake we saw is division by 0. We saw that when you divide something by 0, you get an error. To avoid this, you can use the combination of null if and call if. Null if is a function that turns any argument that equals the second argument to null. We also saw that once you divide a number by null, you get a null. And you can turn that back into a number using call if. The third thing we saw was, third common mistake we saw, is that aggregate function ignore null. We tried to find the number of distinct users that purchased each product, and we found that we got incorrect results for nullable columns. In this case, it was the customer in our sales data. So when you are calculating on specific fields, you need to check that these fields are not nullable. Okay? Next, we saw different ways of working with null. We also saw that when you compare literal values such as string, dates, and integers with null, you can get unexpected results. One way of dealing with it is to use the special comparison operator is distinct from. Is distinct from is using null like an ordinary value. This is very useful, especially when you are working, when you are writing reusable queries where that use placeholders to accept any type of value. So if you need to compare columns that are nullable, you can use is distinct from to compare them safely. Next, we saw an overview of working with dates and times in PostgreSQL. Okay, we saw a bunch of useful functions. We got to know different terms like time zone, epoch, Unix time, daylight savings, interval. We also got familiar with some useful functions such as date trunc, extract, and date part, and interval. We then talked a little about how to work with time zones, and we covered several common mistakes when working with time zones, where the key takeaway from this section was when you are working with time zones, you need to make sure you explicitly set the time zone. Finally, we saw that between is inclusive. When we are trying to compare using between and find values inside ranges of values, we found that it's best to use half open or half closed ranges. Of course, you can use between, but you just need to make sure that you understand that it's inclusive. Before we move on to the next part, I got some questions from many of you about the time zone. So first, I want to ease your mind. This is, it sounds very complicated, but the database is actually doing a very good job at abstracting most of the difficult part from you. So if you use timestamp with time zone data type to represent your dates, you don't have to do anything else besides that. The database is storing dates in UTC times always. The time zone for the query that you run is usually determined by the client application. Or if you are a developer, it's defined by the driver you are using or the ORM you are using. This is what sets the time zone, okay? So the reason that users in LA and New York got different results is because when the client in LA ran the query, he ran it from a client where the local time was set to LA. So we got the results in LA time. When the person from New York executed the exact same query, he got the results in New York time because the client application was set to the local time zone, which is New York, okay? So the reason you need to set the time zone explicitly is that you can't always be sure where your query is going to be executed, okay? So for example, if I send you a text of a query and I won't specify the time zone, I don't have any way of knowing in what time zone this query is going to be executed at. So if I want to be sure about what time zone the result should be in, I need to set the time zone explicitly. Now, if you think about it, most queries you write are usually at a very specific time zone. If you are producing a sales report, this sales report is most likely should be in your local time zone, right? So just make sure that you explicitly set the time zone. Now about the data types. When you're using timestamp with time zone data type, Postgres will store the date time as UTC and will convert it and the client application will convert the date to the right time. When you are using timestamp with no time zone, which is very rare and almost never used, you are responsible to set the time zone for the day. This is why you would normally not use timestamp without time zone. So if you are using timestamp with time zone data type, you are most likely going to be okay. You just need to be careful when you are manipulating dates, when you are adding dates, when you are truncating dates, when you're adding days or hours to a certain date, when you are producing daily reports, weekly reports, monthly reports, you need to make sure that you set the time zone explicitly, okay? So hopefully I answered your questions about time zone. The best practice is to use timestamp with time zone, okay? And if you need to know more about the time zone you're using, I suggest check your client application and how it sets the time zone. For example, in PSQL, I can even show it to you, just so we are clear, okay? You can use show time zone, the time zone, okay? So for example, if this is the time in UTC. Notice that I did not cast this value, okay? This value was cast by PSQL, which is the client application. If I set a different time zone, sorry, let me just open this again, real quick. I'm used to working with Linux, and then when I hit Control C, I'm used to it. I'm used to that. It's clearing my screen. Okay, let me screen share again. Okay, so we use if we set time zone to UTC and select now, we get this time. We can set the time zone to America, New York, and then will get the time now in New York. Okay, so once again, notice that all I changed was the client application time zone, and the database implicitly casted the date for me. Okay, now if I insert now into the database, it's going to be stored in UTC. It doesn't matter how I insert the data is always stored in UTC, but when I fetch the data, I need to make sure to set the time zone correct. Okay, so hopefully this answers your questions about time zones. So you just need to be aware. Okay, moving forward to performance. This is a very interesting part, and hopefully you can gain a lot from it. So let's take a look at the path a query takes when it hits the database. So first you have a connection, which is the connection between your client application and the database server. Next, the database receives the query and goes through a parsing stage. In this stage, it's mostly about checking the syntax. So if you have a syntax error, if you use like select before select, this is where the query is going to fail. Next, PostgreSQL has what's called a rewrite system. This is where things like views are inlined and converted into their SQL representation. We are not going to talk about this stage at all because this is mostly technical stuff related to Postgres itself. Next, the database moves the query onto the optimizer, query optimizer to your plan. This is the interesting part. This is the part where the database tries to evaluate the best execution plan for the query. Okay? Once the database finds the best execution plan, it can move it onto the executor for execution. Okay? So in this section, we are going to focus on the optimizer. The optimizer is one of the most important parts of any database system. This is the part that makes the difference. Okay, this is what determines if your query is going to run fast or slow. Okay, so we are going to focus about the optimizer. Now, there's two types of optimizer systems. There's the rule-based and cost-based. PostgreSQL is cost-based, but to understand what it means, let's talk about rule-based optimizers. Rule-based optimizers are what you intuitively think that the database is doing. Rule-based optimizer can say, for example, if I have a query that is trying to fetch something according to a field that has an index on it, use that index. Okay? It doesn't matter if it makes sense to use the index or not. There's a rule that says that if there is an index on the field, you should use it. So a rule-based optimizer has a lot of rules for a variety of scenarios, and it goes one by one and tries to find the best plan according to the rules. So all database systems used to work with the rule-based optimizer, and newer types of database are moving to a cost-based optimizer. So a cost-based optimizer is working a bit differently. A cost-based optimizer starts by generating all the possible execution plans for a query. The bigger the query, the more possible execution plans there are. Okay? So, for example, if we have a where condition on a field, okay? One way of executing the query is scanning the entire table. This is called a full table scan. If the field has an index on it, the database can come up with a plan to first use the index to find the rows that match the predicate, and then fetch the rows using the index. Okay? So these are the two possible execution plans for a simple query with an index on the filtered field. Now, when you have join, the execution plans determines the order in which these joins are going to be executed at, okay? If you have, for example, tables A, B, and C, the possible execution plans are joining A to B and then C to the result, joining B to C and then joining A to the result, and etc., etc., etc. The more complicated the query is, the more possible execution plans there are. So this process can take some time. As we mentioned, for larger and complicated queries, this can take some time because there are a lot of possible execution plans. The next step, once the optimizer drafted all the possible execution plans, is that it goes on each and every execution plan and it tries to estimate a cost. Now, it's important to understand cost is an arbitrary unit. It doesn't really mean anything. It's just a measure the database used that you can use to compare between execution plans. Now, having said that, we know that one of the things that affect the query most is I/O, okay? There are several metrics that can affect the query, mostly CPU and I/O, but we know that I/O is the slowest. So CPU is usually not a problem. So cost is usually the number of blocks the database estimates it will have to read in order to satisfy the query results. Okay. So it's not exactly the number of disk page fetches or I/O, but it's usually roughly close. If you have, for example, very computational heavy, sorry, one second. If you have a query which is very CPU heavy, the optimizer might decide to add some cost to account for this extensive CPU usage. Okay, so how is the database estimating the cost? How does the database know how many I/Os it's expected to perform? For that, there's statistics. The database maintains a lot of statistics about your tables and your indexes. There's a command called analyze, and there's usually a background job that's called analyze that runs on occasions and collects statistics about your tables. We are going to see some of these stats later, but you need to know that these measurements are not exactly accurate. If the cost says that the database is expecting to fetch 10 blocks, it doesn't necessarily mean it's going to be 10 blocks. This is just an estimate. Okay? So once the database drafted all the possible execution plans and estimated the cost for each one, it chooses the plan with the lowest cost. Because the lower the cost, the faster the query is expected to be. Okay? So before we move on to actually seeing this in action, we need to generate some data. So in your DB fiddles and in your GitHub, there are some commented queries. So I want you to take 1 minute or 2 minutes and comment them out and generate the data. Okay? I have an SQL here. I'm going to go over it. It looks scary, but it generates a bunch of random data. Okay? And I want you to execute this query in your databases so we can see some execution plans with a lot of data. Okay? So take 1 minute and execute this in your database. In the DB fiddle, you have the statements already in there. You just need to remove the comments. It's under generate some data. While you create the data, I want to go over some of the stuff here because there's some pretty nice hacks here that you should know. So to generate some random data that we can optimize, we start with generating IDs. There's a function called generate series. Don't be too scared if you don't understand everything. This is the pretty messy query, but we start with generate series. This function generates a table or a range or a series going from 1 to 10,000, okay? And we take the maximum ID from the sale table and we add it to this series. This will cause this entire block to be duplicated 10,000 times. This is like a table, okay? Next, we are using, we are creating an array with our two branches, New York and LA, and then we pick one at random. You see, we take random multiplied by 2, which is the index, and we use C to pick either 1 or 2. So this will pick a branch randomly. Next, we are using our interval trick to generate solve F. So we take the 1st of March and we add a random number of hours to it, which is 24 times 3 times 6, which is 6 months. 24 hours times 31 months times 6, it's 6 months. This is rough, yeah? I know. Next, we are generating customers. For this, we are creating an array of all of our known customers, but I generate an index in the range of 1 to 30. We only have 4 customers, so this means that the chance of getting a known customer is 4 divided by 30. So in 26 of the times, I'm likely to get null or an unknown customer, okay? Next, we have the product, which is using the same technique, create an inline array, and then you use random to pick one at random. And finally, you have a way, I'm generating a random price at the range of 0 to $150, which is 150 times 100, which is the cents. Okay, and this is the trick to remove the trailing numbers. I want full cents. Okay, so actually I need to create it myself. Give me 1 second. So hopefully you managed to create the data in your databases, because if we want to see some execution plans, we need to see some data. Okay, so you should now have 10,015 rows in the table. Everybody got it? Somebody ping me in the chat so I know that you got it. Okay, so if we want to see an execution plan for a certain query, we can use the command called explain, okay? So if we want to see what the database is doing when we are executing select, that's right, TY, great. If we want to see what the database is doing when we are executing select all from sale, we can use the keyword explain, and we will get a query plan. So this is a very simple query plan. You can see that the database is going to do a sequential scan on the sale table. We are going to break this down a bit more in a bit. But for now, what I want you to remember is that when you use explain, the database is not actually executing the query. Explain just produces an execution plan. So if we remember the chart from before, when you use explain, the database is going only up to the execution plan phase. It will not execute the query. So you can, for example, time this query because you just get the time the database took to produce an execution plan. If you want to execute the query and generate an execution plan, you can use this command, this variation of the command. Explain can accept several arguments. Two that are most interesting, in my opinion, are analyze on, timing on. When you do explain analyze on, timing on, and your query, you get the execution plan. And you also get a few interesting things here. First, you get the execution time, okay? So we can see that this query took 3.5 milliseconds. So the database actually executed the query and timed it for you. It also timed how much time it took it to produce an execution plan. So this is a simple query. So it didn't take the database a lot of time to generate an execution plan. You can see that it took it 0.092 milliseconds to produce an execution plan for this query. And another very interesting thing that you can see here, when you add the analyze on flag, is that you can see how the estimate of the database, which is the first part in parentheses, and then you can see what actually happened. So we are going to look at this in a bit. So hopefully you understand how to produce an execution plan, and you understand how to produce an execution plan with timing. So let's take a closer look at the execution plan. So if you explain select from sale, this is the execution plan we've got. The first part is the command. So what is loops? I'm not going to go into loops, but I'm going to explain other parts of the execution plan. Okay? So we can see that the database did a sequential scan of the entire table. This is called sequential scan on sale. We can see that the database estimated the cost between 0 and 176. Okay, so it estimated that it will need to make 176 fetches from the disk. Now, it's entirely possible that if you run this locally, you got different numbers, because the execution plan is very affected by various storage parameters. But in my case, it's 176 blocks. And it estimated that it is going to get, that the database is going to get 10,015 rows from the table. We know that this is a pretty good estimate because we know that we inserted 10,015 rows into the table. So in this case, the database was pretty spot on in its estimate. Now let's take a look at another execution plan. This time, we want to see what the database is planning if we are trying to fetch the sale for ID 1,000. Okay? We want to fetch the sale with ID 1,000. If you remember, the ID is our primary key. And when you create a primary key in PostgreSQL and any database really, the database is creating an index behind the scene. The index is unique. So when we ask the database to show us the execution plan for sale with ID 1,000, the database used an index called cell.pk. This is the name of the index of the primary key ID. You'll notice that the estimate is now much, much lower. Before it was 176 IOs, and this time it's only 8. The database also estimated that it's going to get only 1 row. So this is pretty interesting. Why did the database expect to get only 1 row? If you think about it, the database used the primary key index, and primary key by definition is unique. So if you fetch a specific ID, which is the primary key, the database knows it can expect only at most 1 row. It's either 0 or 1. So this is an example of what a simple execution plan looks like with an index. Now, we talked about execution plans, and I just want you to know that learning to read execution plans is can be very complicated. I'm doing this for like 15 years and I'm still um, finding it very difficult to read some complicated execution plans. So this is truly something that takes time to master. The more execution plans you'll see, the better you get at understanding what the database is doing and possibly how to improve the results. So don't be overwhelmed by execution plans that you see here or later when you try to fetch some execution plans for yourself. So as we said before, execution plans are relying on statistics. PostgreSQL and most databases have background processes for gathering statistics in the background. Okay, in Postgres there are two main tables that you can look at if you want to see what stats look like. Okay, we can see here I fetched the statistics for our sale table from a dictionary table called PG Stats. And we got some interesting stats here that we can look at. For example, nullFrac is the fraction of the table that is null. So you can see that, for example, ID, the nullFrac is 0. This is because this is the primary key and null is not acceptable. So nullFrac is 0. Sold at, branch, and price are also all 0 because the database analyzed the data and it saw that these fields does not have null values. However, if you look at the customer, you'll see that the database estimates that 86% of the values in this column are null. So if we try to think for a second like an optimizer, if I try to do select from sale where customer is null, when the database will try to estimate how many rows are there, is going to take the 10,015 multiplied by the null fraction, and it will get a roughly accurate estimate of how many rows it's expected to get. So this is the null frac. Another interesting metric here is the n distinct. This metric says how many distinct values are there for each column. So let's take a look at the branch, for example. The branch is 2. We know that we have 2 branches. We got New York and LA. So the database analyzed the data and he found that there are only 2 distinct values in the table. Okay? We can see here some negative values. I'm actually not sure what they mean, but for customers, we know that there are 4 customers, only 5 products, and discount only 5 because when we generated the data, we didn't generate random discounts. Now, correlation is a bit complicated to explain, but I'll try. Correlation is a metric that says how well the data is known. Let me try and draft it over. Correlation says is an indication of how the data is organized physically according to a specific index. For ID, the value is 1. This means that the values of the table are stored, are ordered on disk according to the ID. So if you use range queries on the ID, the database can expect to fetch consecutive blocks. Okay? This is a very important statistics, especially when you're working with advanced types of indexing such as green, but we are not going to talk about this. So for the next part, I want you to create two indexes in your database. I want you to create one index. Okay, so there's an explanation in the group chat about negative numbers for indexing. Thank you, CN. Okay, so in the meantime, I want you to create two indexes on the table. Wait, so I want you to create two indexes on the table. You got the script for them, once again, both in the GitHub repository and in the DB feeders. Just comment them out and make sure to run again the schema SQL. So take a second and do that. In the meantime, I'm going to answer TY. He asked, does PostgreSQL provide any tools or mechanism that suggest how to optimize slow performing queries? So Postgres does not have such a tool built into Postgres itself. I'm sure there are many companies and third-party tools that can analyze your queries and try to suggest ways to optimize them. But I don't know of a tool that is provided by Postgres to help you optimize slow queries. But this is why you're taking this class. Hopefully you'll be able to optimize yourself. Okay, so after you create the two indexes, you can inspect the table. In PSQL, you can do /d stale. In dbfield, this is not available, but you can see that two indexes were added, two indexes of type B3. I included two links here at the bottom left. This is a very long series, not from the documentation. It's called Indexes in PostgreSQL. It's a great series of articles about indexes, B3 and other types of indexes. If you are interested in indexes, then this is a very, very in-depth article. You can click the links here in the presentation, but in the repository, there's a PDF version, and the links are clickable. Okay, so let's start and actually look at some execution plans. Okay, so I'm going to share my screen. Okay, so I just created the index, and we want to see if we can see what an execution plan of the query to fetch bill looks like. So we'll start with explain. Where customer equals bill. Okay, so in this execution plan, we first see that the database used the index called sale customer IX, which we just created, and the database is expecting to get 356 rows for this query. Just to check how accurate the estimate is, let's actually count the number of rows. Okay, so this is pretty accurate. The database also estimated that it will take him 91 IOs to generate this query. If we went to try and see more conveniently what is happening, we can try and use the analyze and timing flags on this. Okay, so analyze on. This will show us a comparison of what the database expected and what actually happened. And we also want to see some timing data. Okay, so now you can see that the execution plan, execution time, was just under a second, maybe third of a second, and the planning time was fifth of a second. Okay, once again, we can see that the index was used. Here you can see that the database expected to get 356 rows. This is the estimate. This part is the estimate. And this is what actually happens. So this is the result of the query. And you can see that the database expected 356 rows, and he actually got 356 rows. Now, if you want a quick tip of how to identify a bad execution plan, when the difference between what the database expects and what actually happens is very high or significant, this means that the database is having trouble estimating the number of rows correctly, and this can cause the database to make wrong estimates about the cost and therefore pick an execution plan that is not the best for your query. Okay? So a big part of what you need to do when you are trying to optimize queries is you need to check that the database actually gets what he expects to get. Or in other words, you want to check that the database estimates are correct. Okay? So we use this query to fetch bills sales. Now, let's look at what happens when we try to fetch the sales for the customer unknown. Okay, so we see that the database now did not use the index. Okay, we see that the database did a sequential scan on state. We see that it expects to get 8,000 or so rows, and the filter is null. So the reason for that, first and foremost, is that B3 indexes are not indexing null values. This is very important. The reason that the database did not use an index here is that nulls are not indexed. This is not the only reason why a database would not use an index, but nulls are not being indexed at all. So back to the presentation, we can see the same thing here. When we try to fetch bill, the index is used. When we are trying to find an unknown customer null, we are doing a sequential scan of the table. Okay, before we move forward, I just want to say, I know that the links are not clickable. Oh, in the PDF slide, the links on the B3 is not clickable. Okay, I'm going to fix that once the class is over. Thanks. So let's take a look at another type of query that uses the customer index. So let's try to fetch the same query, but this time we want to apply some transformation on the field. So before we saw that when we try to fetch bill sales, the database used the index, right? When we did that, the database used the index, and the query ran pretty fast. But what happens when we apply some function? Sorry. What happens if we try to apply some transformation on the field? Okay, so you can see that there are two interesting things here. First, you can see that an index was not used. The database did not use the index. You can also see that the estimate now is very wrong. If we try to run this with analyze and timing, okay, you can see that the number of rows that the database expected or estimated is not like what actually happened. You can also see that the time it took the query to execute is higher. Before it was a fifth of a second, and now it's almost 6 times that. So the reason that the database could not use the index is because the expression lower customer is not indexed. What's indexed is the field customer. So another way of doing this, or the takeaway from this experiment, is that if you want to use an index, or if you want the database to use the index, you should avoid transformation on the indexed field. If you do lower customer equals bill, the index will not be used, okay? So let's take a look at some common mistakes that people make when they work with indexed fields, specifically the type of transformations that can prevent the database from using an index, okay? So I'm going to try and show all of them in screen share. So let's take a look at a query that we saw earlier. Select ID שווה equals 1000, right? Let me also analyze on, timing on, because we want to see the estimate versus the plan, and we want to get the timings. So we can see that expected one row, received one row, and use the index. What happens if we do the exact same query, right? This is the same query. Take a look at that. This time the database did a sequential scan on stale. You can even look at the execution time, much higher. So this is really a shame because you can just as well do this, but if you apply some transformation on the indexed field, you are preventing the database from using the index. So this is a very common mistake that I see of simple arithmetics on indexed field. Another common mistake is, once again, time zones. For example, here we want to use the sold at to get all the sales that were made in 2021, okay? And we can see that the database is doing a sequential scan even though it has an index on sale. But if instead we'll move the time zone to the right side of the equation, meaning will not perform a transformation on the indexed field, the database will be able to utilize the index. And this query on the bottom will run much faster. Before I move on, there's the question about null values asked by TY, and that's a great question, and I want to address it at the end, okay? That's a great question. So another common mistakes related to date is date arithmetics. For example, here you can see that we want to do some weird condition on sold 8 minus 1 day is greater than 2021. This can easily, this part, the interval can be easily moved to the right-hand side of the expression, leaving the indexed field with no transformation. So using, writing this query this way will not prevent the database from using the index. And as you can see, the sold at index is being used, and the query will execute much faster. Another common mistake that I was unable to demonstrate in this table is usually with emails, you can see that people are using lower email equals some lowercase text, okay? And with full names, this is especially common because sometimes the person will include their full name and then you'll do this. I realize that this is problematic, but this is an example of a case where you might be preventing the database from using your index. Okay? So I want to stop here and actually address the question from TY about storing null values and also address this specific problems of email. So when you design a schema, it's usually best to try and avoid null values. It doesn't mean that you can't use null values, but as you saw in this presentation, there's a lot of common mistakes that happen around null value, because null is actually not a value. Null is not a value. Null is used to mark nothing. And doing manipulation on nothing is very obscure. So when you are designing a schema, there are techniques you can use to avoid the use of null. Okay? So for example, in data warehouse environments, if we had to change the way our unknown users are represented, instead of using null to represent unknown user, I think under some circumstances, you can create a fake user and call it unknown. You would usually give him some special ID, like negative ID, like -1 or 0. And this will be a special user. And you will use this user to indicate that this is an unknown user. Okay? Also, you can see that in the table that we currently have, the sale table, we used zeros to indicate no discount. We could have easily used null to indicate no discount, but instead we decided to use zeros, an actual value, to indicate no discount. This is much safer to use actual values instead of null values to indicate no value. Now, if we are talking on data modeling, you can see in this example, these slides show, for example, that we try to find a user by its email address. Okay, so one way to make sure that the index is used is to, when you insert emails into the database, you apply the transformation beforehand. So for example, in this case, I would insert the email in lowercase already. And this way, I can apply lowercase on an input and safely compare it with the value I store in the database. So this is really a data modeling issue. And most of these problems can be solved by modeling the data correctly. So hopefully I answered your question about how to model your tables to avoid these mistakes and whether it's okay or not okay to use null values. Okay, so this is a nice one, which I've seen several times. Okay, thanks, TY. Great. So, union is an operator in SQL that is used to concatenate two result sets. You can see in the top that we are using union all to concatenate two result sets. And on the bottom, we are using union. So it's very important to understand the difference, because if you use the wrong one, you can either get incorrect results or just do work for no reason. So the difference between union and union all is that union all concatenates the results, and union does the same thing, but you remove the duplicates. In order to remove the duplicates, what union will usually do is do a sort. And as we know, sort can consume a lot of memory, a lot of CPU, and it's usually will take longer. So if what you need is union all, be sure to use union all and not union. Okay, so this is just a really, really minor thing that you need to be aware of. So to conclude this section, I want to share one last tip with you regarding performance before we move on to the productivity teams. This performance issue is related to something that is pretty unique to PostgreSQL, and it's called common table expression. Common table expression is a special syntax that SQL has. I don't know if you know it, but in SQL, you can create like an inline table that behaves like a view. I'll try to show it to you. So you can create a table like this, for example, with food, okay, and I do here is that using the WISP syntax, I created like an inline table, also known as a common table expression. And then I used that inside the query, okay? So the important thing to remember here is that in most databases, when you do this, the common table expression is inline, and it's being translated into something like this. So this equals this. This is called inlining. You can see that it's the same result. So in most SQL databases, common table expression is just synthetic sugar for this. It's used to make writing queries easier. But in PostgreSQL, before version 12, these common table expressions are materialized, meaning that when I do this, the database will create a temporary table called food, okay, with the result of this query, and then use it in this query, and use it to satisfy this query. From version 12 and on, what Postgres does is inline by default. So the reason I'm telling you this is that if you are using a version of Postgres prior to 12, as I've seen some of you do, you should try and minimize your use of common table expression, or make sure that what you put inside the CTE or the common table expression yields very, very small results. Because if you see here, for example, in the bottom example, I create a CTE with the entire result of the sale table, and then I use that to find the sale with ID 1. In Postgres 11, this will essentially duplicate the entire sale table. And this will take a long time to execute. If you are on a new version of PostgreSQL 12, then you have nothing to worry about. It's fine. Okay? Great. So let's just do a quick recap of what we've seen in this past section. First, we saw how the database process query. Okay? We focused on the execution plan phase, and we saw how the database generates execution plans and compares between them. We also showed how to use explain, and we did a very quick overview of how to understand what the database is doing, how to read an explain plan, and how to compare between execution plans. Okay? We also saw that null values are not indexed by B-tree indexes. And we also saw different scenarios that by applying transformation on an indexed field, we essentially prevented the database from using our index. So if we can avoid this transformation, we have a better chance of getting a better performance from the database. Finally, we talked about union and union all and the difference between them, when to use each one. And we added a quick note about common table expressions in Postgres versions prior to 12. Okay, somebody asked me about if Postgres have a visual graphical execution plan analyzer. Once again, I don't think, or I know that Postgres does not provide anything like this out of the box, but there are a lot of tools out there that provide such service. For example, I think that there's one tool called PG Mustard that you can look into. It creates that visual execution plan. If you want to study more about execution plan, this may be a good place to start. Okay, so we don't have much time left, and I want to finish up with something fun. We are technical people, and we like productivity tips. So we are going to talk a little bit about ways that we can be more productive writing SQL. So case, we all know case. Case is very useful. We used it before to apply different time zones in our query. And actually case can take many forms. It's the regular form that we study in the university and that you read about in tutorials is the left one. You do case and then a bunch of conditions and what happens in each condition. Like case, when fruit is apple, then red. When fruit equals pear, then green, and so on. This is a lot of repetition. Fruit equals, fruit equals, fruit equals. Case has a nicer syntax, more similar to switch case, if you are familiar with it. You can do case fruit, and then, when apple, then, when pear, then, when, and you get the same result. This is actually a pretty nice syntax, and I'm using it for stuff like that. So next we have, this is a tip that you need to be careful with, but I'm going to share it anyway. Once again, in all of this sense of keeping things dry and not repeating yourself, you can reference column position in group by and order by, or use the alias. For example, in the left side, the red query, you can see that we generate two columns, two expressions, actually. We first concatenate the first name and the last name to produce a full name. This is an expression. And then we have a count expression. Now, if we want to group by the full name and count the cells by user, we essentially repeat the same expression twice. So this is not very good, and it's harder to maintain because if someone, maybe a different developer, goes in, checks out your query, and decides that instead of concatenating with a white space, he wants to do a slash, then he might forget to change the bottom. So a way to avoid that is you can either use the column position, if you look at the right, instead of repeating the expression first name, concatenate last name, I use one, which is the column position, first column. And in the order by, I reference the alias of the count. Instead of writing count, I'm writing cells by user. Now, a word of caution. In production or queries you write for a specific system, I strongly suggest to either repeat the expression or use the alias. Don't use positional arguments, okay? But if you're just writing code like you're using PSQL, you're going back and forth in an interactive session and you want to do things really, really quick, then it's very quick to just write group by one, order by two, it's great. It's very fast. Can full name be used in a group by? I think yes, but you know what? How about you check TY? You seem like a great guy. You check and you tell me. So TY is going to check and verify that we can use an alias in a group by, and we are going to continue on to the next step. And TY will tell us if we can use the full name in the group by. So next, this is my personal favorite. I used to work a lot with Oracle, and Oracle does not have this. And when I switched to PostgreSQL, this and the next one I'm going to show you completely blew my mind. I don't know how I managed without it. It's called selective aggregates. It means that you can apply a filter on an aggregate without actually applying a predicate. This is great for pivot tables. This is great for a lot of things. It's also much, much shorter than writing case statements. So if you look at the left side, we want to count the number of known and unknown customers in our database, right? So on the left, we're using case and some case when customer is null, meaning unknown, then one has zero, okay? And same for known. In the right, you can see the selective aggregate syntax. In special syntax, you write count, which counts the rows, and then you apply a filter and a condition. So filter, open parenthesis, where customer is not. This is almost the same. This is almost the same. Now, there's one thing you need to make sure that you do is that on the left side, sum is going to be 0. If there are no unknown customers, it's going to be 0. On the right side, on the other hand, if there are no rows that satisfy the filter, the result of this can be null. So on the right side, you need to handle the case where count filter where customer is not is null. So what you need to do or can do is wrap this inequalities that we've seen before. Okay? So this is also one of my personal favorite things that I discovered when I switched from Oracle to PostgreSQL. One of the more challenging queries to write, especially, by the way, in job interviews, is finding the first or last row in a group, okay? Let's say, for example, we want to find the last sale made by each customer. If you try to think about it for a minute, how would you find the first row for each customer in the database? So one way to do it is using analytic functions like row number and rank. A better way to do it is to use distinct on. It's a special syntax which Postgres already has, and it lets you basically do like a group by, but without actually grouping the rows, but instead using a combination of distinct on and order by, you can get the first or last row in a group. So the query you see on the left will give you the first sale that each customer made. This is very, very powerful, and I'm using this a lot. Some ORMs also have support for this, and this is very, very useful. I want to, maybe I can show this to you. I don't know if we have any time. We're almost nearing the end. Okay, I want to leave some time for Q&A, so I won't show you this. But I strongly recommend that you try this query and master this technique of using distinct on. It's very, very useful. Okay, so what you've learned. This is the end of our presentation. I want to thank you all for spending the last 3 hours with me. We started by talking about common mistakes in SQL. We worked on a sales database, and we did several exercises to illustrate and show what common mistakes in SQL look like. We also discussed why mistakes in SQL are especially dangerous. And we also focused a lot about working with dates and times. And we explained different terms related to time zones and date arithmetics. We then talked about how to write faster SQL. We talked about the optimizer, we talked about cost-based optimizer, how cost is calculated, what it is, and how to compare execution plans. We touched it very briefly. I think that those of you that think this is interesting, you can dig deeper into it. And then we finished off with some productivity tips, ways that you can be more productive when you write SQL. So hopefully you enjoyed this presentation.